Hello to my Math 110 class at Crafton Hills College. I'm making a video to try to help you better prepare for what you're going to be doing on your third upcoming test here. I know that with the online instruction they do show videos about this, but I always like to give it my bit of a personal touch to kind of show you how I connect the information together and perhaps provide you with an alternative perspective on how to approach these questions here. So we're going to go ahead and start in a way, and this will probably be done in two parts, as I'll need two different times to tape this video to get all the problems taped and complete. So the first question reads as, a survey of 100 fatal accidents showed that in 24 cases the driver at fault was inadequately insured. Find a point estimate for P, the population proportion of accidents where the driver was at fault. Showed that where the driver at fault was inadequately assured. So first off, the notation for a point estimate is a lowercase p with a little hat on top. And the way we calculate that point estimate is the value is going to be with the formula x over n, where x are the number of trials that fit the category we're looking at versus n being the total number of cases being considered, or the sample size, if you will. So note that P has many different meanings in the course of statistics, and in the formulas that you record, you have to note these differences. So in this case here we have a P hat, and that's going to be the point estimate. So in the question here, they mentioned that the survey is done with 100 people, so that's going to be 100. And it says, since we're being asked to show a point estimate for the population proportion of accidents where drivers at fault did not have insurance, we're told up here that 24 of those 100 had drivers with inadequate insurance, so we're going to write that as 24 over 100. And if you're looking at the choices then, if you take 24 and divide it by 100, the point estimate you're going to obtain is going to be 0.24, which is going to yield choice B. Okay, going on, so that's going to be the work for question 1. Going on to number 2. Now, number 2 is going to be a little long, but we'll go through this in some thorough detail here. 22. An article in Florida newspaper reported that the topics that teenagers most wanted to discuss with their parents, the results of a poll show that 46% would like more discussions about the family's financial situation, 37% would like to talk about school, and 30% would like to talk about religion. These and other percentages were based on a national sampling of 522 teenagers. Estimate the proportion of all teenagers who want more family discussions about school. Use a 99% confidence level. Okay, so we're asked to estimate the true proportion. Okay, so the true population proportion. So the first thing we need to do is we need to come up with a point estimate. All right, so we need to, or sorry, I take that back. They give us a point estimate for this, but what they don't tell us is the x value. So first off, the question's asking, because it's a little wordy, it says estimate the proportion of all teenagers who want more family discussions about school. So what we need from here is which of the percentages provided above correspond with being the point estimate for wanting to talk about school. And that appears to be 37%. So in question 2, the P hat is going to be equal to 0.37. Another thing that we're also going to want to know is how many teenagers did they talk to? And they talked to a total of 522, so that's going to give us N is going to give us 522. The formula as it's provided for in the book, and as was shown in the last question, is that P hat is equal to X divided by N. Another handy formula to kind of keep in hand for a situation such as this when they're not giving us the value of X is to simply take what we get if we cross multiply this formula as such. So if I cross multiply this, 1 times X will equal P hat times N, or just 1 times X will be X Well, x will equal p hat times n. We know p hat, we know n. We need to know x for the work that we're going to be doing here. So x will then be equal to 0.37 times 522. And when we calculate this out, this is going to give me 193.14, and of course that's rounding a little bit. But since we're talking about x values, we need to have this rounded to the nearest whole number, since we are going to be talking about people. So x is going to get rounded to 193, and this is the value of x we're going to use. In terms of rounding rules, when we're figuring out x in relation to a point estimate, we always round the x value to the nearest whole number. So generic rounding rules apply. So now that we found this, we can go ahead and put this into the calculator now and find this, what this is. So when we put this into the calculator now, we want to find a confidence interval for a population proportion. I want to make sure that this is visible to everyone here, so I'm going to put this up just a little bit more. Okay, I'm going to take the question off, which you should have anyway. So to put this into the calculator, we're going to hit Stat, and then we're going to go over to Tests. And because we're doing a population proportion confidence interval, we're going to arrow down in the calculator here a little bit. We have Z interval, we have T interval, 2 samples Z interval, 2 sample T interval, 1 prop Z interval. This is what we're looking for right here. So we're going to go ahead and press enter. You'll see the information that is being requested here. I already have this in my calculator from the work I was doing before. So at this place, we put the x value, which is 193, the n value, which is 522, and then the confidence level, which in this question, I think I typed another question in, so I changed my confidence level here. It's not going to be 0.95, it's going to be 0.99. So make sure I have the correct confidence level in. And what the calculator is going to provide for us is going to give us a confidence interval. And we're going to be able to use this confidence interval in order to obtain the point estimate as well as the margin of error, which is required based on the form they're asking us to express this answer in. All right. So what I'm going to do is I'm just going to take this value and write it down as I see it right here. So I'm going to write down here, this is going to be 0.31531 to 0.42416. So what I'm going to go ahead, I'm going to work with these two items, and I'm going to find the value of p hat, and then I'm going to find the margin of error. Now, we know that we can find p hat by taking the x over the n, but what we're doing here is, based on the data we've collected, we're finding what that's going to be here. So I'm just reviewing my notes on something a second here. Well, yes, the p hat they've already given us is 0.37. So it's going to be the margin of error that I'm looking for. Now, but let's say, for example, they didn't provide you with the p hat. Let's just go ahead and say they provided you with x and they provided you with n. Another way that you can find p hat is to take the confidence interval that's generated. So we take the upper limit plus the lower limit, and we can divide by 2 to find the point estimate. Now, if we do this, we're going to get 0.37. So we already know what that is. If we want to find the margin of error, we take the upper limit minus the lower limit, and we divide it by 2. So from the problem, we already know what the point estimate is, but what we need to find now is the margin of error. So we can go ahead and take the difference of these two numbers, and then divide the difference by 2. So this is going to be 42416, 0.42416 minus 0.31531 divided by 2. Now, if you're doing this on a calculator, just one thing you want to be careful about. Oops, let me put this in here. I'm going to go ahead and enter a parenthesis here. So that proper order of operations are followed. And then I'll divide that by 2. And you're going to find that to the nearest hundredth, that's going to be 0.054. So for my margin of error, I'm going to have for this now is equal to 0.054. So now when I write this answer, the confidence interval as PE plus or minus E, I can write this as 0.37 plus or minus 0.054. And that one is going to be, if I'm not mistaken, that should be choice A. Making sure that everyone can see all the work here. Okay, there's all the work in its entirety for that question. Again, for this one, you don't have to calculate p hat as it's already provided in the question. However, you just want to be sure that if you're not given the point estimate and that you're given x, this is another way to calculate it based on the confidence interval you obtain from your graphing calculator. Yeah, and that's the work for question 2. Question 3, a private opinion poll conducted for a politician to determine what proportion of the population favors adding more national parks. Let's see here. How large a sample is needed in order to be 95% confident that the sample proportion will not differ from the truth proportion by no more than 4%? Okay. So this question is, what is the sample size? So a couple things to consider. One, you need to understand that the question is asking for a sample size. And the second thing you need to consider is that it is asking for the sample size of a population proportion. So, because there are different formulas for when it's asking for a population mean, or if it's asking for the sample size of a mean. So, n is going to be equal to z of alpha minus 2. Using that critical value, that's going to be squared, times p hat times q hat. And that's all going to be divided by the margin of error squared. Now, the formula may look a little bit different in the book, where they have this quantity divided by this quantity squared times p hat q hat. You can use either formula you want. I just choose to write it this way, and then we're going to show how this gets put into the calculator. So first off, there are certain critical values that when you're comprising your cheat sheet, there are certain ones that are probably good to just have handy. On the test, you will be provided with a z-score table so that you'll be able to utilize the z-score table to calculate critical values on the test. But there are some good ones to keep handy because they emerge a lot in statistics. So for the first one, if you're using like a 95% confidence level, and that's CL for confidence level, then what we'll have is that the z of alpha divided by 2 is going to equal 1.96. So this would be something that would be really handy to keep on your sheet. And by the way, another thing to mention too, remember that if we have a 95% confidence level, the alpha value, that's going to be equal 1 minus the confidence level that's going to be used in the problem here. So just thought I would mention that detail. If we have a 90% confidence level, z of alpha divided by 2, the z-score that we're going to be using is going to be 1.645. Now, this is accurate to the nearest 3 decimal places here. And this is something you don't actually find on the z-score table. It's one of those that falls just kind of directly between 2, and you kind of take the average. So this is another one that's good to have. If you have a 99% confidence level, then the z of alpha divided by 2, that's going to be equal to 2.576. And you want to keep these handy just so you kind of fall back on these, so you can refer to these. Okay. Well, now that we have these down, we should be able to obtain most of the rest of the information for the problem. So we have this value, what it's going to be. P and Q is not provided in the problem, though. Like, they don't provide us with a prior point estimate that may have been derived from other previous studies. And if that is the case, which it is for question 3, we may assume that P hat is equal to 0.5. Now, in your book, they'll sometimes write this as p hat times 1 minus p hat. And if you want to go with it, that's certainly fine. You can do that. Other textbooks and other videos you may see online will write this as p hat times q hat. And just as in previous chapters where we're learning about binomial distributions, and p is going to be the probability of success and q is going to be the probability of failure, well, q hat is equal to 1 minus p hat. So basically, q hat is the complement of p hat. So if p hat is going to be 0.5, then q will be 1 minus 0.5, which will be 0.5 also. Okay, so if p hat is not given, then we make the assumption that it's going to be 0.5. The impact of this is that it creates a situation in which we obtain the largest possible sample size when p or q are known to ensure that we get the most accurate answer for this question for n. And finally, for the margin of error, well, that's something they provide for us. They tell us what a margin of error no more than 4%. Now, if that's 4%, we just need to make sure that we're writing this in our problem as 0.04. Okay, so there are three pieces that we have to be kind of cognizant of here when we want to determine the sample size of a population proportion. The z-score we need, the p hat, the q hat values, and then the margin of error, making sure we write this as a decimal. Okay. Now that we have that done, we'll go ahead and we'll figure out the value of n. Let's kind of block some of this off. So we'll have n is equal to, in this case, because we're looking at a 95% confidence, or a confidence level of 95%, we're talking a z-score of 1.96. That's going to be squared. It's going to be times p hat times q hat, or 0.5 times 0.5. You may have a formula in the book that shows this as being just 0.25. When it's unknown, 0.5 times 0.5 is 0.25. And then the margin of error is going to be 0.04 squared. Now, when you're typing this into the calculator, if you're going to try to do this in one calculation, that's good, but just be careful what you're doing. So we're going to need a parenthesis for the entire top. So let's have one parenthesis. You're going to have then 1.96, and I'm going to use the square function here, okay, times 0.5 times 0.5. And now I'm going to box it off the top entirely. The calculator will know to do the exponent first before it multiplies through. And then we're going to divide that by the quantity of 0.04 squared. And then if we press enter on that, we should get an answer of exactly 600.25. Now, when it comes to sample size, 600.25 is the minimum number, meaning that if we go lower than 600.25, that it's not going to be the minimum number to be sure. So we can't round this down to 600. When it comes to the values of n for a sample size, we must always round up. So for the value of n in a sample size, we must always round up. And when we round up, that's going to give us 601 as being our minimum sample size in order to answer this question. And that's going to be choice A. Looking for a fresh sheet of paper here to continue our work. Going to go to question 4 now. Construct a 95% confidence interval for the population mean. Mu. Assume the population has a normal distribution. A sample of 25 random English majors has a mean test score of 81.5 with a standard deviation of 10.2. Round to the nearest hundredth. So this is how the game works with this. So if you are told the population standard deviation for a question like this, if you're told the population standard deviation explicitly, then you're going to use what's called a z-interval. If you're not told what it is, then you're going to be using a t-interval, the t-interval function on the calculator. Now, in the question, when it says a sample of 25 English majors, a sample of 25 randomly English, I don't know if that sounds right or not. It has a mean and a standard deviation. So unless we are explicitly told that this is a population standard deviation, we may assume that this is a sample standard deviation. It has to be explicitly clear that this is a population standard deviation. Otherwise, we may assume it's a sample standard deviation. Okay? So what information are we working with here? So for question 4, we are told that n is equal to 25. We're told that the sample mean, okay, so we're looking for x bar, that's going to be equal to 81.5. We're told that the sample standard deviation is equal to 10.2, and it wants us to develop a confidence interval with a confidence level of 95%. So for this, and then we'll just write down the confidence level is going to equal 0.95. And we're going to go ahead and put this information in, and the calculator should give us a nice value for this. So how do we do this? We're going to go to Stat, we're going to go over to Tests, and we're going to arrow down. Now the z-interval, choice 7, that is what we use when we are told the population standard deviation. You're going to hear me say this a lot. If you're not provided with a population standard deviation, then you have to use what's called a t-interval, because this is going to rely on what's called a student t distribution, which is usually what's used in these circumstances. So I'm going to press enter here, and there are 2 types of input that could be sought. One is if we're given data, and one is if we're given stats. The only time we're going to use the data, and I'll highlight that so you can see it, the only time we're going to use data is if we're given a table of data that we have to utilize in order to calculate this. But here they're just giving us the main stats. They're giving us the sample size, they're giving us the standard deviation, they're giving us the mean and the confidence level. So they're giving us everything we need. So I'm going to press enter to highlight stats, and then I'm going to provide all the information I have here. So I'm going to have x bar is equal to 81.5, comma. I have my sample standard deviation, which is going to be equal to 10.2. I have my n value, which is going to be equal to 25, and then my confidence level, which is going to be 0.95. So what are we putting in here? We're using a t-interval. Okay, stats is the input. X bar is equal to 81.5. Sample standard deviation is equal to 10.2. N is equal to 25. And then the confidence level is equal to 0.95. And when we go to calculate that, notice that the calculator, when it gives it to us, it gives it to us to 2 decimal places. Your test may ask you for some different level of rounding. It should never ask you for a level of rounding more than what the calculator will give. So when we put this in, we get 77.29 to 85.71. And if we look at our answers for this, that's going to correspond with answer 8. And that's how we use the graphing calculator in order to find the confidence level, in this case for a population mean. Okay, so one thing to keep in mind that this is not the same thing as working with a population proportion. And in most cases when we're working with a mean, you have a choice between whether to use a t-interval or a z-interval. And we only use the z-interval when we know what the population standard deviation is. And that needs to be clearly provided. Question 5. A doctor at a local hospital, bring that up again, at a local hospital is interested in estimating the birth weight of infants. How large a sample size must she select if she desires to be 99% confident that her estimate is within 2 ounces of the true mean? So if you're looking at this, you have to recognize that this question is asking about a sample size, and specifically that it's asking about the sample size required for a mean. So this has a formula too. So n is going to be equal to z of alpha divided by 2 times the population standard deviation divided by the margin of error, and all this quantity is going to be squared. So we're going to determine everything that we can derive from this question. So what's important here? What do they tell? We know that there's a 99%, we want this to be, we want to be 99% confident, which means that we require a confidence level of 99%. Why is that important? Because that helps us determine our z-score. And as we mentioned earlier, that if you have that information down on a table, a confidence level of 99% corresponds to a z-score of 2.576. So that's what I'm going to put in for z of alpha divided by 2. In this question, they also specify that. Now, here's the one thing that this question was a little off about. It says that the sample standard deviation is equal to 7, where they should be providing this as a population standard deviation, which we're going to put into here. So we're going to assume that's equal to 7 here. And then our margin of error is going to be within 2 ounces, so that's going to be equal to 2. And we're going to take that value, we're going to square it. Again, being careful with what you put into the calculator. If you do that in one fall swoop, you want to make sure to properly use parentheses. And if you come up with the answer, we're going to get 81.28. And again, that's the value of n, so we're going to have to round this up, so we get 82 for a final answer, and that's going to be choice C. Okay, let's take a look at number 6 now. Construct a 95% confidence interval for the population standard deviation of a random sample of 15 crates which have a mean weight of 165.2 pounds and a standard deviation of 10.4 pounds. Okay, so this is, in this case, when we talk about a standard deviation, we're talking about the sample here. Okay, so when we're putting this together here, this is going to be the sample standard deviation. In this question, we're looking at the formula for number 6. When we're figuring out the confidence interval for a variance, there's a formula for this. I'm going to use that here. So that's going to be our population standard deviation. And you're going to see it's going to look pretty similar on either side. This is going to be, under here, the square root of n minus 1 multiplied by the sample standard deviation squared divided by chi-squared of alpha divided by 2. And then you'll have less than or equal to n minus 1 times the sample standard deviation squared divided by the chi-squared value of 1 minus alpha over 2. So in this type of problem, because we're looking at the standard, we're trying to measure or develop a confidence interval to measure the true population standard deviation. Standard deviation in its distribution is not normally distributed. It also needs to be further stated that that when we use a chi-squared distribution, that a chi-squared distribution is not symmetrical. So these are values that we will need to obtain from a table. And I do have a copy of the table here that you'll be able to utilize, and I'll show you how to utilize this table. So unfortunately, the calculator is not going to be able to do this one for you. So here is an instance in which you will need to know how to utilize these formulas. Okay, so first off, let's get some of these values in here, and I'll kind of walk you through the rest. First off, n is going to be the sample size, and we know from this question that n is going to equal 15. Okay. We also know from the question that the standard deviation is going to be 10.4. You also notice that in this question they give you a mean, and in this question, this number is only serving as a distractor. It's not going to be helpful in performing any of the calculations that you need to do to obtain a confidence interval for determining the true population standard deviation. And then we have a confidence level of 95%. And that confidence level is going to be important because it's going to help us determine what values we choose here. So we'll have, in this case, 15 minus 1. And if you wanted to just put 14, that's probably going to be a lot easier to work with. Then we'll have times 10.4 squared. And that's going to be the same thing over here. 14 times 10.4 squared. It's these two values that I want to talk about looking at a little bit here, okay? So for this one, we're actually going to work out how we identify what, how alpha over 2 plays a role. So if we have a confidence level of 0.95, I'm going to kind of do just a bit of separate work on calculating this below. So I'm going to bring this up here. I'm going to take the confidence level of 0.95, and the way I determine alpha, let me bring this whole thing up a little bit here. I determine alpha by taking 1 minus 0.95. If I do that, that's going to give me an alpha value of 0.05. So if I have an alpha value of 0.05, then in order to obtain the values that go here, and then consequently over here, I need to take for this one 0.05 divided by 2. And what that's going to give me then is going to be, I need the chi-squared value for the area of 0.025. So that's the first one. And for this other one over here, it's going to be 1 minus this. Which will give me, chi-squared, I should say. The chi-squared value of 0.975. So we need to know what these values are going to be here, and now we have these. Okay, so hopefully we've done the work with the z-score and using a normal distribution, that this part won't be too difficult to understand. But if you need further clarification, you can always shoot me a question about how to do this. But there are a lot of videos on how to do this as well. The other thing you need to consider is one thing known as what are the degrees of freedom. And the degrees of freedom are important because just like a student t distribution, a chi-squared table or chi-squared distribution changes shape depending on the value of n, or depending on the number of samples. The higher the value of n, the more it begins to resemble a normal distribution, but it doesn't ideally fit that, so it's not symmetrical. So we have to know the degrees of freedom for this. So if we want the degrees of freedom, that's going to be equal to n minus 1, which in this case is 15 minus 1, which is 14. So we have 14, we have this value, we have this value. So we're going to use those two values here to work with the table that you're going to be provided with on the test to determine what values are going to go below here. So because we're looking at degrees of freedom here and we have 14, this is the row we want to focus on right here. Now we have two values that we need to, when we talk about the areas to the right of the critical value here. We have the 0.025 and then we have the 0.975. So going down here, where the alpha divided by 2 is equal to 0.25, we're going to use the value of 26.119. And then where we have the alpha divided by 2 equal to 0.975, we have the value of 5.629. So these are the two values that are going to go into the denominator here. So this is going to be 26.119. Now you may see that the chi is squared. That's how it comes in the formula. We don't need to touch that. We don't need to square that. And then the value that's going to go over here is going to be 5.629. Now again, be careful with what you're doing with these. Make sure that you're using parentheses properly. Okay, and if we do that, we're going to get for this, round to the nearest tenth, is going to be 7.6, and over here is going to be 16.4. So if we're going to put this in parentheses properly, just to kind of give you a hint, I guess I'll try to show you all this, and let me see here. Just trying to get all of this work into one picture here so you can see this. And I think I've done that. All right. So how would I put this into the calculator? Let me show that here. So I'm just going to show you the first example because the second one's going to look pretty similar. And that's my warning to know that I'm going to stop the video once I'm done showing this question. So I'm going to produce part 2 later. So I'm going to type in, when I do this now, I'm going to type in a radical. And notice here is parentheses. Okay, so it'll be 14 times 10.4 squared Okay. I'm going to add a second parenthesis here. Because what I want to be able to do is I want to be able to take this quantity on top, divided by what's at the bottom, which is going to be 26.119. And now that I add a second parenthesis here, I have one set of parentheses to just keep the whole top together. And now I've got a second parenthesis here that keeps everything under one radical. And then when I... Oh, yeah, okay. Let's try that again, shall we? So second parenthesis, 14 times 10.4 squared, close, divided by 26.119, close it off. Let's press enter. And lo and behold, I do in fact get 7.6141 and that gives me the 7.6 I need. If you don't want to go through too much work, hit second, and then enter. And then all you have to do is go back and change the second number that you have in here, and that will be like, 5.629. Hit enter, and that'll give you the 16.40 or the 16.4 that we have. And this is going to be the confidence interval to determine the true population standard deviation of birth weights of infants. And in this question, that's going to be choice D. Now, I'll be coming back with a video to go over the remaining questions in a little bit.